Okay, hi everyone. My name is Martin. I'm a research scientist at Google Research on the flood forecasting team. And while we get the slides up there, maybe I'll just say, so what I want to cover in this talk is kind of an overview of the work that we've been doing around hydrologic modeling, but also inundation mapping or inundation modeling, and kind of more general, the work that we've been doing on flood forecasting at sort of a global scale. We can kind of break that down into, I guess, three broad components. I'll talk about two of them. I'll start with the riverine floods, which is our, historically has been our main focus. And I'll talk both about the hydrologic modeling and the inundation modeling. And then more recently, we've also started to look into urban and flash floods, or more pluvial kind of flood scenarios. And I'll cover that one as well. And then we have a third, much more younger project around coastal floods. I'm happy to talk about that offline, but I won't have the time to go into that here. So let's start with the riverine case. I think probably most of you know we run deep learning models for hydrologic modeling, and the model that we use is an LSTM, or long short-term memory network. You've probably already seen a bunch of posters or workshops around this. I think there's another one later today. And so just if you're not familiar, kind of a very high-level overview of how this works. Essentially, we run a lumped setup. So for every basin that we want to make a prediction at, we feed the model a one-dimensional time series of precipitation and temperature and various other meteorological variables for that specific basin. And then in addition to that, we feed the model with what we call catchment attributes, or static attributes. And those are things like, I don't know, the soil type, elevation, maybe land cover. So anything that might affect how the model responds to precipitation and how it converts that into stream flow, or how the basin responds to that. And so we feed all of that into our LSTM, and we train it by backpropagation to predict stream flow at any given point in time. So that's a very, very short overview of how the LSTM works, but that's kind of all you need to know for the purpose of this talk. Now what's kind of different from classical hydrologic modeling is that we don't train this model specifically for every basin that we want to make a prediction at, but rather we train a single model for kind of the entire world. So basically, we try to collect all of the basins that we can possibly, or all of the streamflow records that we can possibly get a hand on, and we train a single model on all of these locations that you see on this map here. So this is what we trained our current operational model on. You're seeing about 16,000 basins, or 16,000 gauge locations there. Most of those are part of Caravan, which is an open source data set. And we train a single model on all of these, and in doing that, this allows us, or this makes the model learn sort of generalizable behaviors of streamflow response, and so we can actually apply that model to all of the places where we also don't have streamflow, which is kind of important because one of our big goals is providing flood forecasts for places that don't have existing warning systems, or that don't have existing flood forecasting systems, and those tend to be the places that also don't have historical streamflow records. So the model becomes actually quite good at transferring its knowledge across space and making predictions in these places that we don't have historical records at. So that's all nice, but there's of course also a bunch of limitations, and I just want to quickly cover sort of one of them that we currently are sort of working on. And that is the limitation that everything that I've talked about so far is lumped modeling. So what that means is, no matter how large the basin is, we still just feed it a single dimensional time series of the meteorological forcings and also of these static catchment attributes. So the model has no idea in a large basin like this one. This is the central European Danube basin. The model has no idea if the precipitation is happening all the way upstream, and so therefore the rain or the water will actually take some time propagating down the river network and until it reaches the outlet, and therefore it takes some time until it affects the streamflow response. Or if the rain is happening all the way downstream, and therefore the streamflow response will be kind of immediate. The model just doesn't know. We're kind of withholding that information, and so the model is probably also less accurate than it actually could be because it just doesn't have any information about that spatial heterogeneity. Now this is not a problem that's kind of specific to deep learning models. This is something that hydrologists have been kind of struggling with for a long time, and there's also a solution for that, a known solution, and that's distributed or semi-distributed modeling. So the idea here is that we break down the big basin into lots of small subbasins, and we know the connectivity of the river network, so we know how each subbasin drains into the next downstream one, and so on. And our idea now was, can we transfer this lumped deep learning setup into this semi-distributed or distributed setting and train an end-to-end deep learning model that is actually aware of all these differences that are happening in all these different subbasins. And so that's what we've tried to do is where we look at this subbasin network as a graph, where every node is a subbasin and every edge is a river reach that connects two subbasins. And what we can do then is we can actually run our LSTM model at the subbasin scale. So basically, we train one LSTM to run at each individual one of these nodes, which is, I'm showing this on a toy example here, where we have just 3 subbasins that are connected to each other. And so we run the LSTM on each subbasin, and the task of this LSTM is now to predict the local contribution of water from that subbasin to the overall stream flow. And once we have that, we can actually run sort of a little neural network that along the edge, or like a routing model that predicts how the water gets delayed as it travels down the river reach. So we do that, and then in the downstream node, all we need to do is just aggregate the incoming water plus the local contribution of that subbasin, and now we have a prediction at the sort of one level down subbasin, and we can recursively keep doing that until we reach the overall outlet of our river network. And so in doing that, we can end-to-end make a prediction for a whole river network in a deep learning fashion, so the whole thing can be trained in one go, and we get a model that is now aware of the spatial heterogeneity inside of the bigger basin, and that still has all of the benefits of the deep learning models, meaning it still works really well in ungaged basins. So we actually hope to make this our operational model in the next coming months. We're generally seeing pretty good results, especially if you train it at a global scale. It really outperforms the lump modeling aspect. There's a lot more I could talk about here, but I want to switch gears a little bit and talk more about inundation modeling, because that's also kind of the theme of this morning. And for inundation modeling, things are actually a little different than they are for the hydrologic model. What you see here is our map of places where we currently do inundation forecasts, or where we provide inundation information. It's actually not forecasts everywhere. And you see that you actually don't see a lot of purple or like a lot of colored places. So there's a huge part of the map where we don't actually have inundation information at the moment in our model. And part of that is because the hydrologic model doesn't work super well everywhere. But a big part of that is also that we don't actually have historical SAR imagery. So most of this relies on SAR imagery, and we just don't have good quality SAR imagery during historical flood events in many of these places. That is either because just the satellites didn't happen to pass over during flood events, or that is because these places are in urban areas where SAR imagery doesn't work well, or mountainous areas, or so on. So this is kind of a problem. And so the model that we currently have is extremely simple, where basically what we do is we feed the model information from SAR imagery. We could also use optical imagery, but for the most part we use SAR because it has less issues with cloud cover. In addition, we feed it the information from our hydrologic model. So this is what's called here the Gauch percentile. We convert the hydrologic model prediction into like a percentile space so that it's more uniform across different places. And in addition, we feed the model some long-term information about, like, is this a pixel that is just always wet, or is this a pixel that is only rarely wet? We feed all that into a neural network, which is really a tiny feed-forward network, and we make it predict the forecast of inundation for that location for the next couple of days. But you'll notice that this model doesn't actually, like, you don't see any elevation information in this model. So, and that is because we're training that model for every location separately, and so therefore we can kind of bake in the elevation information into the weights of the neural network. But that comes at the cost of this model not being transferable to other places. So it works like reasonably well if we have SAR information or SAR imagery at a given place, but there's just no way how this model would learn to make a prediction in a place that we haven't trained it on. So this is different from our hydrologic model, which is really good at that. And so more recently, we've started a project where we try to copy some of the things that we do in the hydrologic model and try to do them as well for the inundation model in order to get to a point where hopefully we'll be able to sort of fill the map that I showed in the beginning and have inundation forecasts in more places. And the way that we're doing this is mostly based on sort of computer vision, or more recent computer vision models where like things like vision transformers, where the idea is that most of what you're seeing here, like the task of inundation forecasting, is really a computer vision task where we have historical or previous or past SAR imagery, and we want to forecast how that SAR imagery evolves in the future, given additional information around the elevation, given additional information around the gauge forecast, and so on. So this is a pretty early project. We don't actually have like real results to show yet, but we're kind of hoping that this would allow us to to broaden the coverage of our inundation forecasts. In the last couple of minutes, I want to talk a little bit about our work on urban and flash floods. We had heard in the first talk today how important that actually is, being able to not just predict riverine floods, but also these sort of quick onset floods that are more driven by just the sheer amount of precipitation. And the problem that we're kind of facing here is that if we want to train a deep learning model, we kind of need some sort of target variable that we use to train our model. And for riverine floods, it's kind of clear. We have like worldwide networks of stream gauges where people have been measuring stream flow in many cases, for decades. And so that's a kind of a nice setting where it's pretty easy to train a deep learning model on that. For flash floods or urban floods, it's kind of not even clear what that physical variable would be that we would train the model on. Not only don't we have records of it, we don't even know what that variable would be. And so we had to get a little more creative here. And the solution that we came up with is that we actually train this model on information that we derive from news articles. So this is maybe a little more out there, but it turns out to work pretty well. So what we do is, Google is pretty good at scraping the internet. I think you mostly know that. And so what we do is we scrape the internet for news articles, and we pass them into Gemini. So we pass them into an LLM, and we check whether, or we ask the LLM to tell us whether this is about a flood. And if so, then when and where did that flood happen? And what the output of that pipeline is kind of a structured data set of locations and timestamps where flooding happened over historical periods where we have news articles. And then we can take that structured data set and use that as the labels for our machine learning model to train the model. And essentially, the model now predicts whether on a given day there will be a newsworthy flood happening in that location. So the pipeline looks something like this, where the inputs to the model are pretty similar to what we do for our riverine model. So we still feed it information about the weather, the forecast of the weather, and some sort of static characteristics. But then the labels of the model, or the training labels, are quite different in that those are just a binary classification of will there be a news article about this location and this timestamp within the next 24 hours. And now this might seem a little weird and maybe might seem a little weird to you if you're used to like physical modeling and you're used to having these like tangible physical variables that you model. But it's actually quite nicely aligned to the purpose of the model here, because the thing is meant to be a warning system for flash floods. And so it makes sense that we predict exactly those kinds of events that people write news articles about, because those are exactly the kinds of events that have affected people, and so the ones that people would like to know about. And so it turns out that this actually works quite well. We've compared this to a number of flood warning systems around the world, and it tends to be pretty good at predicting these kinds of floods. The caveat is that, of course, the resolution is not as high as you would have it in like a hyperlocal system that might use maybe radar information from the specific place. But the advantage of it is that it works sort of globally. And you can see that in sort of this map here, which shows the coverage of this structured data set that we've extracted from the news articles. We call it the ground source method or data set, where you see essentially the whole world is covered by news articles about flooding. So these are, I think, about 2.6 million flood events that cover more or less the entire world. Of course, there are certain biases in there due to just the amount of news coverage of any given place. But we still think that it's pretty good to cover, to use this as sort of training levels. And beyond that, I think I'm kind of excited about this because I think we've heard about someone talk about wildfires. I think the general method of this strategy to derive information from just the public internet is actually something that could be useful beyond flash floods or beyond floods in general, and be useful for other sort of earth science processes or other kinds of environmental disasters. Okay, I lost my last slide. There There we go. So I'll end here just with a couple of resources. Maybe the one I'll point out that might be interesting to a couple of folks here is the second one, which is our recently released GitHub repository for deep learning and flood forecasting. I think many of you already know neural hydrology, which is kind of a researchy Python package that we wrote a long time ago and that we still maintain. But the problem that neural hydrology has for more operational use cases is that it doesn't support it doesn't support forecasting. So it doesn't support like making lead time predictions. And so we've now created this second repository, which is exactly geared towards making lead time forecast predictions, and it replicates the models that we actually run operationally in our forecasting system at Google. I'll end here, and I'm happy to answer questions either if you have time now or after in the coffee break.